To jeszcze raz w takim razie witamy i po krótkich problemach technicznych zapraszamy na wykład Ewy Grabskiej-Szwagrzyk na temat obserwacji Ziemi. Wykład będzie się w języku angielskim, jest pierwszym wykładem w ramach kampusu kreatywnego Direction Earth Space. I zapraszam w takim razie już bez zbędnych przedłużeń, przekazuję Ewie głos, a po prezentacji będziemy mieć oczywiście czas na pytania.
Okay, good afternoon, good evening, everyone. I hope that you can see my screen and you can hear me well.
Yeah, we can see your screen.
Okay, great. Okay, so I have a pleasure of this short lecture, giving this short lecture about Earth observation in general. And I will start, I hope that you will enjoy it, of course, and this, for those from you which never worked with satellite imagery, it will be easier to understand how it works. And I will start with some short explanation or short definition, because we are talking about Earth observation. I think this term is pretty clear, but I will just say that it generally refers to gathering information about our planet, and usually it is performed using remote sensing technologies. And what does it mean that this is remote sensing? Remote sensing is generally acquisition of information about some objects or phenomenon without making physical contact, so just from the distance. On the other hand, we have, for example, ground studies, in situ studies, right? But we often in Earth observation use these remote sensing techniques. And there are also different types of remote sensing. So it can be from satellite, which is interesting for us today, and it is called satellite or spaceborne. It can be performed from airplanes or drones. It is called airborne, and also from the ground. It is called terrestrial remote sensing, for example. And in this short lecture, I will focus on spaceborne Earth observation, so basically on satellite remote sensing. And I will start with very short history, because I think it's quite interesting. Of course, the history is much longer than from the 1946, because it wouldn't be possible to develop without, for example, invention of camera. But here I wanted to show you the first photo taken from space, so-called space. It was taken in 1946 by V2 missile, which was actually a German rocket, German missile captured by the Americans. And after the war, they taken this first photo, which is here in this slide. You can see that the quality is not very good, but generally you can see the Earth, the part of the Earth. And it was taken from approximately 105 kilometers, so just above the beginning of outer space. So not so high, but still it is considered as a space. And what happened next? So you probably know that the era of satellites began in the 50s. So there were this first satellite called Sputnik 1. It was launched in 1957. After that, NASA Explorer was launched in 1958. However, these satellites did not take any photos of the Earth. And the first satellite designed for Earth observation was called Vanguard 2. It was launched in 1959. It was launched by Americans as well. And generally, it was quite experimental still. This Vanguard was supposed to take measurements of daytime cloudiness, but the data turned out to be not very useful. And also the process of putting that Vanguard in the orbit was quite long, because before this Vanguard 2, there were 4 other Vanguards which failed to reach the orbit. After that, year after that, there was the first full-scale weather satellite called TIROS-1. It was in 1960, and you can see in this slide the photo taken from TIROS of the Earth, some clouds, and so on. And what happened next? Of course, there were more and more satellites, and there were weather satellites. After that, there were satellites which were focused on monitoring the Earth. And here I wanted to mention about first space-based Earth observation system called Corona. It was American. It was actually a reconnaissance system. So reconnaissance satellites used to spy Soviet Union, China, and other areas between 1959 and 1972. And actually, you can see the picture, a photo taken by this Corona satellite on the left side. This is the image taken in 1967. And comparison with nowadays or 2004. And generally, it is really interesting that nowadays more and more Corona imagery is used in scientific studies because so many things changed during this past 50 or 60 years that we can now analyze the changes. For example, it is used for some ancient or prehistoric site detection and so on. And finally, NASA with US Geological Survey actually launched Landsat-1 mission in 1972, and it is also a special mission that I will talk about it later, but it was special because it was like the first mission to monitor Earth's land. It was, of course, the quality of the imagery or the resolution was not so high, but still it was kind of a breakthrough milestone in the development of Earth observation. And yeah, that's about the history. Of course, only very short, some basic facts. And now I would like to say a few words about how does it work, how the satellites are taking picture or acquiring data, information about our planet. So firstly, I want to tell you that there are two broad categories of techniques. So we can say about passive and active techniques, remote sensing techniques. And passive sensors use naturally emitted light from the sun, reflected from the Earth's surface, or in some cases also emitted by the Earth's surface. So you can see in the simple image here that there is the satellite, there is the sun, but satellite and the sensor aboard the satellite only measure the reflected energy, right? And on the other hand, we have active sensors, and they operate with their own source or emission or light. And you can also see this simple picture, which satellites actually emit something, and then it is reflected from the Earth or from some objects and comes back to the satellite. And I will start from passive remote sensing, because I think in case of spaceborne techniques, it is more commonly used. It is also probably easier to use. And this passive remote sensing, as I said before, the sensors aboard satellite, onboard satellite, passively receive the radiation reflected or emitted by the target. For example, different objects on the Earth. Not only reflected from the sun, but also emitted in case, for example, of fires or lava flows. Some energy is also emitted, actually. And the sensors measure something which is called radiance, which later is converted to actual reflectance. And you can see this image here. It is very, I think, basic, but it is important to know that the image which is actually collected by the sensor is not like ready yet for using that, because there are different effects in the atmosphere, such as scattering or absorption, and they should be corrected before using such data. And therefore, there are also different levels of products, raw or after pre-processing. For example, some calibration or atmospheric correction. And probably in most of the cases, you don't have to worry actually about this image and these effects, because you already can get or use process images. But however, you need to be aware that this is not so easy, that like there is a camera in the space and it's taking pictures and send them to us. Okay, So that's how it works. Still, in passive remote sensing, there are some important things that I need to say, because passive remote sensing, the sensors in this passive remote sensing operate in particular parts of electromagnetic spectrum. And you probably know there are different parts of electromagnetic spectrum. For example, there are visible waves, which are seen by the human eye, but there is also infrared, for example. We cannot see in infrared, of course, but satellites actually can. So the sensors, these passive sensors, use visible wavelengths like red, green, blue waves, but also infrared waves, which are between 700 nanometers to 1 millimeter. And this infrared part of the spectrum is also divided into some smaller parts, which are called near infrared. So this near part, SWIR, which means shortwave infrared, and TIR, which means thermal infrared. And actually, the part of the spectrum which is used by passive sensors is shown here in this image. Also, there is some ultraviolet, because some sensors actually also measure energy from this ultraviolet part of the spectrum. And this parts of the spectrum used by passive sensors is usually known as optical remote sensing. So I will probably also use this optical remote sensing term later in my presentation. And here you can see just the typical image taken by a Sentinel-2 satellite. And this is actually true color composition. There is only visible light here. You can see the image of some agricultural fields. For example, there is some rapeseed field. There are some rapeseed fields which are yellowish greenish. And generally, if you go to a plane and will take a photo from that plane, you will see something similar, right? But as I mentioned in the this passive Earth observing sensors, we also use infrared. And in each so-called spectral band, the intensity of radiation in different wavelengths is measured. So, for example, what does it mean? That the sensor separately measures the reflectance in visible blue region. So, yeah, there is a sensor and it measures radiation only from 448 to 510 nanometers. And after that, there is another band, spectral band. And in this band, only the waves from 500 something to 500 something nanometers are measured, and so on and so on. So this is important that satellite sensors measure the electromagnetic spectrum in different parts, in different waves, but separately. And we got this spectral band. Later we have this, of course, as I mentioned, infrared and so on and so on. This is just an example image here. And here I wanted to tell you why we use different bands, why we use, for example, this infrared and so on. And this is actually, this can be observed in this simple chart. It is called spectral curve, and because each material or object interacts with electromagnetic radiation in a different, unique way, it leads to differences in the reflected or emitted energy. And you can see these spectral curves. There are 3 types of objects or land cover. We have water, soil, and green vegetation. And on the y-axis, you can see the value of reflectance. So how many % of the signal in specific waves is reflected. On the x-axis, you can see the wavelength, so in micrometers. And for example, take a look at water. Water is usually rather dark in the satellite imagery. Why is it so? Because as you can see, water reflects some energy in the visible part of the spectrum, but rather small amounts, like 10 15%, you can probably see that here. Invisible light, okay, it reflects some energy, especially in green and blue bands. But after that, in near infrared part of the spectrum, water has near zero values in reflectance. What does it mean? Water does not reflect any near infrared. It absorbs all of the near infrared into water, right? So, typical spectral curve for water will look like that. But also remember that if we have like a shallow water, if we have water which is full of algae or which is full of transported material from solar floods and so on, the spectral curve will look different because it, for example, will be more green if there are algae and so on and so on. And the same is with two other types. For example, green vegetation has very unique spectral curve. You can see that there is this small peak in green because of chlorophyll, because green vegetation has a lot of chlorophyll. But after that, you have seen that the reflectance is very, very sharply increasing in near infrared. Exactly, green vegetation, which is healthy, which is dense, reflects a lot of near infrared. When, for example, some plants start to be unhealthy or start to die, or there is autumn and the chlorophyll or leaves are turning to other colors, this spectral curve will also look different. So, for example, the reflectance in this near infrared will be lower for unhealthy plants. Therefore, we can just study using satellite imagery consisting of this different band. We can study different objects, but also the small changes in this object. The same is with soil. If you have dry soil, if you have wet soil, the spectral curves will be different because, for example, wet soil is a bit darker usually. So that's how it works. And it's like a basic of remote sensing studies, I guess. And yeah, let's move on. I hope it's clear, more or less. Still in passive remote sensing. And as I said, there are the spectral bands. And sensors has multiple spectral bands, like 10 or 15. And in this case, where there are multiple spectral bands, the imagery is called multispectral. It's quite obvious. But there are also some special sensors, which have, for example, 100 or 200 or 300 bands, right? They are very narrow. They has to be narrow because they only like measure the reflectance or the waves in very, very narrow bands. But in this case, we say about hyperspectral imagery, and this is actually depicted in this photo, in this image. Multispectral imagery, we have, for example, 6 bands in different part of the spectrum, and we have something like reflectance in each of these bands, which is not continuous. But when we look at this hyperspectral imagery, we have hundreds of bands, so we can also get continuous spectrum. So like the spectral curve that was on the previous slide. And what happened if we have these bands? So we have different spectral bands and we can combine them into different color compositions. Because, for example, if you ever worked with or will work with satellite imagery, you will, for example, download the data and you will see that each spectral band is like a separate image. And if you open that in some GIS software, it will probably be in some grayscale as it is shown here. So the grayscale meaning the dark pixel represent low values, white pixel, bright pixel represent high pixel values, right? So we have these separate bands, but the very powerful technique is to bring them together, right, into one composition. And actually, on the computer, we have 3 colors, RGB, right? So we can put or assign separate bands into each color on the computer. For example, in this example here, you can see that band number 3 was assigned to blue color, band number 4 was assigned to green color, and band number 5 was assigned to red color. And the composition from this three bands looks like this. So the image on the right side. It is very red and might be not very easy to interpret at the beginning, but if you start to work with satellite imagery, it's become more and more clear why is it so red. And I will also tell you on this next slide why there are sometimes different red colors on the imagery. And here you can see different combinations. So I put actually Sentinel-2 imagery into compositions. And this one, so in the upper right corner, there is so-called true color composition. So basically the same as human eye can see. So we have visible red assigned to red color, visible green to green, and blue to blue, right? So you can see this is a part of the Polish city of Gdańsk. There is the Baltic Sea, there is this built-up area infrastructure, there is Vistula River, there are some forests, but also some agricultural fields, and basically it's easy to interpret, right? But I also put here two false color composition because I told you that we have this near infrared and shortwave infrared. So we need to, or for some reason, the spectral bands are there. And actually, if you put such composition with, for example, near infrared assigned to a red color of the computer, you will get something like that. Why? Because you can see that there is red pixels here represents vegetation. And a moment before I showed you the spectral curves, and there was this green vegetation. Green vegetation has very high reflectance values in near infrared. So if we put near infrared as a red color, then the vegetation simply will be red in the image. We have also different types of land cover here. You can see, of course, the Baltic Sea and the river, and they are dark because a lot of almost all of these waves from infrared are absorbed. We have also some infrastructure, which is usually quite bright. It reflects a lot of energy. And another example of false color composition, this time with short wave infrared as a red band, near infrared as a green band. So now we have different sets of colors, different palettes, which is also at the beginning maybe hard to interpret, not very intuitive, but actually using this different false color composition make it sometimes make it easier to analyze some stuff. For example, here you can see this forest in the western part or here by the sea are actually there are coniferous forests and there are broadleaf forests. And for example, in this true color of composition, there is no difference. They are just dark green. But in this composition, false color composition, the broadleaf forests are much lighter, much brighter than coniferous. Coniferous are darker green, and so on and so on. So we can use these extra spectral bands for some more specific analysis. Okay, let's move on to final slide in this passive remote sensing part, because it's also, I think, important. I talk a lot about the spectral stuff. Now I will tell you about spatial stuff. So you know probably that every image has its resolution, right? So also satellite imagery have different spatial resolution. Spatial resolution is just the size of the smallest pixel, right? The pixel in the imagery. And here you can see the comparison of very high resolution image, which is approximately 1 meter. So 1 pixel, the smallest unit is 1 meter by 1 meter square. In the middle, we have Sentinel-2 imagery in 10 meters resolution. And finally, Landsat imagery with 30 meters resolution. So it's getting more and more coarse. You can see, especially in the case of Landsat, a lot of pixels, big pixels. And that's the very important property of the satellite imagery. And probably you know very high resolution imagery from platforms such as Google Earth or Google Maps or other like that. Also, aerial imagery is very similar. So if we look at the Google Earth, there's also aerial imagery in high resolution, spatial resolution. Okay, so that's it about passive remote sensing. For now, I will move later to some applications and products based on that. But now, shortly, I would also like to tell you about this active remote sensing technique. So, as I mentioned before, they use sensor operating with their own source of emission or light. And typically, in this space-borne active remote sensing, microwaves are used. So waves which are longer than infrared. We have visible, infrared, and after that we have microwaves. And microwaves are used because they are relatively independent to weather conditions. For example, they are independent of clouds, right? And they can also operate during nighttime. So there is no need to of sunlight, right? Which is impossible in case of optical imagery, which is actually based on reflected energy from the sun. And the most common use in space-borne remote sensing type is radar. So you probably know radars also from some other applications, but there are also radars in the space, which actually take photos of our planet. It's very maybe not a photo, but something which also shows us the different properties and different objects on our planet. And here you can see actually the example of comparison between optical imagery and radar imagery. So optical, obviously, on the left, radar on the right, and radar sensors used in space, so on board the satellites, are often called SAR. It means synthetic aperture radar. It means just the radar sensor which is installed on a mobile platform such as satellite or aircraft. So it's like synthetically this aperture, this antenna is bigger. And sensor emits microwaves toward the Earth and collects something which is called backscattering, so resulting backscatter signals. And after that, there is analysis of the signal delay and the distance between the sensor and the surface object. It can be determined in this way. And the resulting image is something like that. It is this backscatter signal. It is considered as more difficult for me also because it's more complex than optical imagery. The physical properties and this backscattering is more complicated, more complex. Also, raw images are often hard to interpret and a lot of pre-processing has to be done before obtaining some information from them. However, there are many advantages of using SAR or radar because, as I said before, they are not sensitive to clouds. They can be acquired during the night, which is very, very important for some applications. And see here the example of SAR imagery. Actually, I think it became even more popular after the Russian invasion because there are different like studies showing, for example, the positions of some military staff, right? So here you can see, for example, some analysis performed by somebody just before the Russian invasion. And someone or some artificial intelligence recognized different objects connected to military, like armor and so on. And another example is shown here. This is also connected to war, actually. Here you can see Russian warship in Sevastopol, Crimea, and some AI ship detection algorithms were used to detect and actually differentiate different classes of ships there. So it is quite interesting. Sometimes for human eye it would be impossible, but we have AI as well. And of course, SAR imagery is not only used for the war purposes or detecting some ships or tanks, it is also used in other types of application. And there is something which is called INSAR, which is interferometric SAR. And this is the technique used for mapping, for example, ground deformation, displacement, using 2 or more radar images. Because if you have like 2 images of the same area, 2 SAR images of the same area, collected at different times, you can actually calculate what is the difference between the sensor and this object. So in this way, we can actually study the displacement of the ground. It is particularly useful in some remote areas, like for example, for volcanoes monitoring or earthquakes as well. But here you can see an example of analysis performed in San Francisco. And actually there are some displacement up to 20 millimeters per year, right? Of course, you have links next to every image, so you can later check that if you are interested. And that's all about SAR for now. Let's move on to selected satellite missions, because I hope we already more or less understand how it works, what are these 2 different types of remote sensing. So now selected satellite missions. Of course, there are many satellite missions. Here I only provided some examples. I already mentioned about Landsat. I will tell you more about that during the next slide. I will also tell a bit about MODIS, which is actually sensor, about Sentinel, which some of you probably know, and also a few words about very high resolution data. And let's start with Landsat, which is actually very special. So as I mentioned at the beginning, it was the first Landsat was actually launched in 1972. So we have like more than 50 years legacy, right? So we can analyze the differences till the 70s, since the 70s till now. And this is NASA USGS program. There were many Landsat satellites. Actually, now we have Landsat 9. And at the beginning, their sensor were obviously not so developed as nowadays, because, you know, there is a development in technique. So the first Landsat did not acquire so good quality imagery, but still it is a very important source of data. And now we have actually 3 Landsat satellites in the orbit, Landsat 7, but this is kind of broken since a long time. But we have Landsat 8 and Landsat 9. Landsat 9 was launched last year, 2022, and these both Landsat 8 and 9 are equipped with very special sensors. The first one is called operational land imager, and it generally acquires data in visible and infrared wavelengths. And the spatial resolution of Landsat of this data from OLI is 30 meters, so pixel size is 30 meters. But there is also another sensor, which is called thermal infrared sensor. Its spatial resolution is a bit lower, it's 100 meters, but I will show you in a moment how the data from this sensor can be used. And here you can see, of course, the image showing the timeline of Landsat satellites. This is very long mission, very special mission. Let's move on to Sentinel. Sentinel is actually from ESA, or actually behalf of the joint European Space Agency and European Commission initiative called Copernicus. And it's the series of satellites, different ones. So it's not like Landsat, which is focused, all of the satellites are focused on optical imagery. Here we have different satellites. For example, Sentinel-1 is equipped with SAR, so it's radar. We have Sentinel-2, which is optical and focused on land monitoring. Sentinel-3 is also optical, but also has some other features. It is actually, the optical imagery is of lower resolution than in case of Sentinel-2, spatial resolution. We have Sentinel-4, which is actually not yet in the orbit, I guess. it's not like all of them are in use. And we have Sentinel-5P precursor, which is focused on air quality monitoring, and Sentinel-6, which is an altimeter, and it is used, for example, to assess the changes in the global sea level rise and so on. And now, two special, or maybe two selected Sentinel satellites. Sentinel-2, which is special for me because I work a lot with Sentinel-2 data. It's a European mission, of course, consisting of two twin satellites. We have Sentinel-2A and Sentinel-2B. They are more or less twin satellites. The sensors are almost identical. It has a high revisit frequency. So, for example, at the equator is 5 days, but actually, for example, in Poland, one place is monitored once in every 2 or 3 days. So even more dense time series can be obtained. It has the optical sensor called MSE, multispectral instrument. It operates in 13 spectral bands in different resolutions, but the highest resolution is 10 meters. And here, just a simple impression of this satellite. So Sentinel-2 is quite special, but there's also Sentinel-5P that I wanted to tell you about. This is the first mission dedicated, Copernicus, a European mission dedicated to monitoring the atmosphere. It maps the entire planet every 24 hours, and it is equipped with tropomy instrument. It actually operates in wavelengths between ultraviolet, also ultraviolet is monitored, and the shortwave infrared. And here you can see example of products or of the features that are monitored, for example, methane, nitrogen dioxide, carbon monoxide, and so on and so on. And the example of data from this tropomy from Sentinel-5P, maybe you also saw some examples like that, because during the pandemic, during this particularly this period of March and April 2020, we were, as you remember, probably all of the people were actually sitting home, and many studies have shown changes in air pollution. For example, in nitrogen dioxide concentration due to this pandemic lockdown. And here you can see the simple GIF showing the nitrogen dioxide tropospheric column between for March and April 2019 and 2020. So the difference, the decrease is quite impressive. It's approximately minus 50%. Another data. So Sentinel it's like a European MODIS. Again, it's from NASA, but MODIS is something also something very special. MODIS is the name of a sensor, actually, not the satellite. So Sentinel and Landsat are names of the satellite, and MODIS is the name of the sensor. It is an abbreviation for Moderate Resolution Imaging Spectroradiometer, and this is the sensor aboard two satellites called Terra and Aqua. And they view the entire Earth surface every 1 to 2 days. They obtain the data with coarse resolutions from 250 meters to 1 kilometer. Most of the products are in this spatial resolution, but you may think that it's a low resolution, but they are really useful in continental and global scales. Also, which is very interesting, there are many ready products derived from MODIS, for example, related to land, to the oceans, to the lower atmosphere. So it's not like we only get this image or separate bands. There are also many products from MODIS which are useful in such a broader scale. Here you can see the global surface reflectance from MODIS, composite for the entire Earth. Of course, there are a lot of clouds, and it's probably during the winter because we can see some snow. And example of another product from MODIS, it's actually global vegetation changes from MODIS. This is something called normalized difference vegetation index, and the higher, so the greener area here, it means just healthier, denser vegetation. So vegetation can be monitored using this data. It's obviously that you can see the growing seasons because it's from multiple years, how it changes during the year. So it's also very interesting. And that's all about missions which are open. So Sentinel, Landsat, and MODIS are open access data. They were, for example, Landsat was not always open. People used to pay a lot for a single Landsat image, but now it's open. We can download it, we can pre-process that, process that in the cloud, and so on. But there are a lot of missions which are actually commercials from private companies. And the first high-resolution commercial imaging satellite was called IKONOS, and it was launched in 1999. And actually, you can see some part of the New York Times and showing the part of the Washington, D.C. It's here, and it's titled A New Era in the Sky. So it was also kind of a milestone. It was like a first commercial mission. In 1999, actually, it was also you needed to pay for Landsat data. So it was not like that. So satellite imagery was not so commonly used, but here was the first commercial mission. And there are a lot of these commercial missions. Probably some of you may have heard about some. And for example, there are missions which are using something called nanosatellites or even microsatellites, which are even smaller. Nanosatellites generally are below 10 kilograms. So they're very, very light, very small. And here you can see the comparison. For example, there is a very popular company called Planet, and they have like 100 and something or hundreds of satellites, nanosatellites, which monitor the Earth every day. Very dense time series with high spatial resolution of 3 to 5 meters. And you can see this Dove satellite is very small. It's the first one here. In comparison to, for example, Landsat or some satellite called Worldview 3 is something completely different, right? Worldview 3 is also a commercial high-resolution mission. Another example of nanosatellite or company that use nanosatellite is ISA. It's a very interesting company, Finnish company, and they produce nanosatellites, but not with optical sensor, but with SAR sensor. So this radar imagery is obtained using that. And these are only the examples. There are many, many different missions which are commercial. So it means that in most of the cases, you just have to pay for the imagery. However, probably for some educational purposes, sometimes it can be obtained for free or with a discount. Okay, so that's all about missions. Actually, not all. I will still talk about missions, but now I would like to show you some specific applications and products from different satellite data. And let's start with the measurement of the temperature. So, for example, using satellites, we can measure something which is called land surface temperature. And here you can see example of such products with this land surface temperature. It's not like the air temperature, but land surface temperature. And these studies shown here on these images are derived from Landsat thermal bands. I mentioned when I was talking about Landsat, I mentioned that Landsat 8 and 9 are also equipped with TIRS sensor, which is thermal infrared sensor. And using these thermal infrared bands, we can calculate actually land surface temperature, which is very important nowadays, as you can see, for example, in an assessment of urban heat island. And here are the two examples of this data. On the upper part, you can see the city of Indianapolis. Some some satellite imagery right on the left, and land surface temperature in Indianapolis. It's in Fahrenheit, but still you can see that red color is higher temperature, blue color is lower temperature. And actually, if you compare these two images, you can see that the built-up infrastructure is characterized by higher temperature, and for example, lakes or forests are characterized by lower temperature, which is quite obvious, of course, but it can be actually monitored from space, which is very, I think, powerful tool. And another example in the bottom part, it's the, I think, yeah, it's New York City shown here. And here is the comparison between the vegetation. So the brighter, lighter green means sparse vegetation, while dark green means dense vegetation. And we can compare that with the temperature. And again, of course, the places which are covered with dense vegetations tend to be cooler than the ones which have, for example, no vegetation. So it's also from Landsat data. And what else? So I mentioned Landsat has a very long history, so we can use that imagery for monitoring long-term changes. For example, in this example here, the Maroni River on the border of Suriname and Guyana, shown in 1993 and 2021. So there is very big difference. There are some mining activities, mining operations here, which not only change the land cover, but also cause the this muddy water here, right? So you can see that a lot of mud of some material are flowing into the river, and it's actually also changing the environment there. Another example of analyzing long-term changes with Landsat is the expansion of the cities. You probably know that Las Vegas is more or less in the desert, and it was much, much smaller in the past. Here you can see Las Vegas in 1984. It is not true color composition, so you can see that the colors are quite strange, but you can see this area here of the city, built-up area, is much, much smaller than here in 2007. So the expansion was very, very large, and we can monitor these long-term changes with Landsat, for example. What else can we monitor? We can monitor floods, for example. And here, I'm coming back to SAR imagery, to radar imagery. Radar imagery is, as I said before, very, very special because you don't need to worry about the clouds or the night time. And here you can see the analysis of floods in Bangladesh from Sentinel-1, so the SAR imagery. So during the floods, usually there are a lot of clouds actually. So using SAR, I think it's a good solution. And another good example of using SAR, again, this is Sentinel-1 mission with radar, is showing the glaciers, or actually the movement of some berg in the Antarctica. It was analyzed in August. So actually during the nighttime, because as you know, there is a nighttime in Antarctica during summer, and it is not important for SAR, it just monitors the Earth. So this very, very large berg is moving in this simple GIF, and we can also perform such analysis using SAR. And what else? Maybe something more funny or not, but we can also discover, or actually scientists can discover, new penguin colonies from space. And you can see this image here. Satellite imagery from Sentinel-2 have revealed that there are nearly 20% more emperor penguin colonies in Antarctica than previously thought. So the scientists have used satellite data, Sentinel-2, to track penguin 1, also just penguin 2, and to track the new colonies. And actually the darker area here on the Sentinel-2 imagery show the place where penguins were. So they were moving and they were pooping. So we can see that from space actually. And another example, monitoring agriculture, of course. Generally, satellite imagery is used in monitoring vegetation, forests, but also agriculture. We can monitor or determine different crop types, for example, determine harvesting times, but also plant stress, plant health. And there are pictures here. There are actually two pictures. One Kiev. The Kiev is showing part of Spain, showing the crops, the landscape, how they changed, and different crops grow and different rates and so on. And the image showing the part of Czechia near Prague, the capital city, and there are different types of crops determined, actually classified, right? So that's also a very important application. And what else? Now maybe more in global scale. You can see simple GIF, simple animation showing the sea surface temperature. Actually, the sea surface temperature is monitored from satellites already since 1981. So it's one of the longest satellite-based records of any Earth climate variable, so which is pretty cool. And these are actually measurements from different sensors, different satellites, but you can see, maybe I run it one more time, you can see how nice is this effect. It showed how the temperature changes during the year, but also how the sea currents are moving and so on. And this is also a product from satellite imagery in global scale. What else? Fires detection, for example. There are actually, I need to mention that, maybe I will mention that now. When you work with satellite imagery, you not necessarily need to work on satellite image itself, because there are many products that are already developed. So there are products, for example, product called Fire Information for Resource Management System, FIRMS, and it distributes near real-time active fire data from different sensors. For example, from MODIS as well, which I already mentioned. So there are already products or data that you can use derived from satellite imagery, not necessarily the raw images, right? And this product distributes near real-time data, which is very interesting, because having something which is in real time or near real time is actually very good if we want to do something about like do some activities. Yeah, we can see where the fire is, so we can perform some activity. And here you can see the screen that I took from this FIRMS product on July 13th. And these orange squares represent detected hotspots, so simply fires. So they are detected, and in the background as a base map, I put the actual image from MODIS or other imagery, and you can see that it is perfectly well detected, because from all of these orange squares you can see the smoke is coming. So it is a nice product, I guess. You have the link here, of course. And another product which is very interesting is called Black Marble. Maybe you've heard about that. This is product from NASA, and it is product which has a resolution of 500 meters, and it's like daily global data, daily, but during the night, of course. And it is acquired using some visible infrared imaging radiometer suit, called VIRS. This may be not important, but there is this product, we can also analyze that. You can see the part of this image here, which is quite popular, so maybe you saw that it's the Korea, right? So South and North Korea, and this very striking difference between the light pollution, of course, between these two countries. And another example of using Black Marble is shown here. It's actually before and after Hurricane Michael, and you can see that the Panama City in Florida, town in Florida, before Hurricane Michael was like normal, and after that the light in many parts of the city were actually not working. So it is also an interesting application of this product. And finally, my final slide about Sentinel-2 based products, because as I said, we can use not only imagery, but also open access products which are derived from the imagery. And for example, in different applications, you may need to use some land cover data sets. For example, if you are focused on forest, you can obtain like a forest map and just, you know, make your extent of your area smaller, only clip to forest max or whatever, but also for other purposes. And there are many different land cover products, but there are two very interesting products in 10 meters resolutions derived from Sentinel-2. The first one is called ESA World Cover. It is produced for 2020 and 2021 for the whole globe, so it's global land cover map. And there is also a very interesting product which is called Dynamic World. It is actually automated approach for globally consistent and high resolution near real-time land use and land cover classification. This is near real-time because you actually can select the dates and check what was the land cover during these dates. So also for the, for example, past month or whatever. So I think it's also interesting. You can see the links are here, and there are many more applications, many more missions, and we can, of course, make it longer, but I hope that the most important stuff were here in this lecture, and I hope that you enjoy it, and I hope that for those of you who weren't familiar with satellite images or Earth observation, it is now more clear. And here you can find my email, but also my Twitter, Facebook accounts. And of course, if we have time for questions, I will be happy to answer. And here is the photo, it's an image from Sentinel-2 showing delta of the Lena River. It's in Siberia, and it's just like a work of art, actually. It's a delta during the winter time, so you can see ice and different river mouths and so on. I think it's really beautiful, so I just decided to put it there. And yeah, that's all from my side. Thank you for your attention, and yeah.
Thank you, Ewa, so much for this, and I think we can move to the questions part. So I'm sure that after this like huge portion of knowledge, you probably might have some questions that maybe there is something that you want to clarify or something that intrigued you in what Ewa was presenting. So if you have any questions, please use the raise hand function, and we will start a queue. Or you are overwhelmed by what you
Maybe.
It can be also like a loose comment or something that was, if you want to share what was interesting. Oh, I see, Paulina, that you're raising your hand. So yeah, you can start.
Yes, thanks, Ewa, for a super interesting lecture, and it was loaded with information. Actually, it's crazy how many things you can read from.
That's true. Yeah.
So our team is farm to table, and I saw several slides that they were about agriculture. But how would you recommend us to start with such data? What would be the first step for a group that deals with agriculture? And it's obviously connected with the climate, but maybe you can tell us, like 3 first steps or suggest something. I'm not saying that you have to know the answer, but maybe just, a small suggestion first would be amazing.
So yeah, I think that there are some possibilities that you can use. For sure, I will. Tomorrow I will say about some tools and methods, so you will know also where to get the data. But for now, I think that using the easiest way is to use satellite imagery like Sentinel-2 and different indices, for example, they are like very simple transformation of imagery, which, for example, show the plant conditions. So there is this normalized difference vegetation index. There are also some indices which are focused on water stress or water conditions. So you can use that. And yeah, I think that's a more broad topic that we can discuss also later, because yeah, for now it's just like my basic idea was to use indices.
Yes, that's great. Thank you very much.
Thank you.
Thanks for that. Is there anyone else who would like to ask something or comment in any way or share? Oh, Faustina, I see your hand raised.
Firstly, I wanted to say that it was an awesome presentation. I haven't know about a lot of things, so thank you for that. And I came with one question when you showed the pictures of Russian and their weapons on the sea.
Yes.
And I wondered then, is there any places that are in some way forbidden to look at, or there are politic problems to look at that places? Because I know that some countries are more cautious about it, and I wonder if it's also a matter in the satellite.
I have never actually, thank you. I'm glad that you like my presentation. I actually never heard that there is some problem with satellite data. Of course, with high resolution aerial imagery, it is like impossible to monitor some places. But I guess like missions like Sentinel or Landsat are, just the satellite have their own orbit and just monitor the Earth, right? So I don't think that in this case it's a problem. But as you could see, there were some imagery from Russia and so on. So yeah.
Okay, thank you.
Thank you.
That was an interesting one. Okay, Ola.
Hi. First of all, thank you for the lecture. It was super interesting to listen to that. You mentioned that some of the pictures or some of the images can be almost live, shown, streamed, whatever the right word is. So my question is, I guess, what does that mean, and how quickly we can actually see what's going on? What is the time when taking a picture and us being able to see something?
Yeah. So actually, for example, Sentinel or Landsat, I think they're like available in the same day. For Poland, for example, Sentinel-2 imagery is taking photos around 9 or 10 in the morning, and in the afternoon you can already see this imagery in this, for example, downloading platforms. So it's, I think, quite fast. However, if you have clouds and optical imagery, you cannot see anything, right? So you cannot see through the clouds. But also radar imagery from Sentinel-1, for example, is also, I think, quite actually like up to date, like 1 day or 2 days after. So it's not like a real time, but it's so-called near real time, because you have like quite up to date data.
Mm-hmm.
Mm-hmm. Is there, so then the follow-up question, is there a way to see, I imagine those are not, it's not like a video stream, right? It's a stream of data. But in any case, is there a way to see it somehow live?
Like a live stream?
Sort of. I mean, it's, or maybe it's a,
I don't know if there is like an open access imagery, but maybe there are some movies from the people on International Space Station, but I don't think that there is something like that. Like this, yeah, you can prepare like animations, but they are like not like live. Like for example,
post product, right?
Yeah.
Okay.
Like from several days or months, you can see the differences where something is built or whatever.
All right, thank you.
Thank you.
Definitely the Sentinels are better at live streaming than we are. But yeah, okay, Mateusz.
Yeah, so thank you for your presentation. And I've got a question. You've mentioned that there are many missions that provide us with free satellite data. And then is it possible for the organizations or companies to generate revenue through monetization of the free data?
I wonder one day I wondered about that, because, for example, it would be nice to I create this imagery of Poland and put it on my fan page, and so many people were asking, oh, it could be so nice to put that into a frame in a large format, right? So I also wondered, and I once asked about that someone in European Space Agency, and this person told me that there's no problem in selling that, but actually I haven't done anything with that. So you need to be, maybe you should ask someone from the ESA or NASA if you want to sell that product. But yeah, someone once told me that, but I've never tried to sell stuff
Of
like
course.
cups or something with satellite imagery.
Yeah, okay, thank you.
Thank you.
Thanks. And then we have Martyna.
Hi, can you hear me?
Yes.
Thank you for the presentation. It was amazing, and I'm really excited about that. I have a question about sound, because I work with sound in general, and are there any satellites or missions that collect data about sound and, for example, noise pollution on Earth in cities or something like this?
Actually, I'm not specialist in this part. I only focus on optical or waves, like electromagnetic waves. There is, for example, light detection, like using lasers, but I haven't heard about sound detection. So sorry, I cannot tell you more about that.
Okay, thank you very much.
Thank you.
If I may, I think I could answer that. It would be quite difficult, I think, to measure sound from satellites, because there's not a lot of air where those satellites are. So I think there would not be too dense, like I don't know, the space could not travel through such a spread out gas, which is up there. Yeah, sorry, just want to say that.
It's okay. Yeah, it's probably very complicated to, do something like that.
Mm-hmm. Okay, so I think next person is Carolina.
Hi, thank you. I really loved the presentation, and I was wondering, you probably enjoy sharing knowledge and you're really passionate about your subject. Have you ever had the thought that you stumbled upon something that you think more people should know about? Like, oh, I wish that the public knew that they can check this and this so easily, or something like that. Something that you would want to popularize.
Actually, I have this feeling that my activities are sometimes noticed by people. There are some news in the internet that uses this Polska Sentinela imagery, and I feel like, yeah, it could be for a bigger scale, but it's always nice when someone like appreciate your work and show it to some other people, and people are usually kind of impressed how many things we can see from space. But yeah, maybe in the future it will be even more developed, like the sharing of this the knowledge will be more broad. Yeah, but thank you for your comment, and I'm glad that you enjoyed my presentation.
Thank you.
Okay, and the last person that I can see in the queue is Anastasia.
Hi. First of all, thank you for your presentation, for your time. It was really interesting. And I was just curious, what happens with satellites that are out of use?
So I think they somehow, actually, I haven't read about that, but there was, for example, Landsat 5, and they stopped working with him. And I don't know actually if they destroy him or they change the orbit so it would fall into the atmosphere and burn. Actually, I have no, maybe someone else know about that.
Yes, may I, Szymon?
Yes, sure.
Ewa, maybe you could display some kind of application, space debris. We can see their animation, how many satellites are around our globe. Space debris.
A lot, yeah.
So usually we are trying to deorbitate the satellites which are broken or out of date.
That's good that there are no more debris